All right, we're here with Josh Reich, the inventor of Pyretic. We're here with Josh Reich, the inventor of Pyretic, and postdoc at Princeton. On to great things after that, I'm sure. And thanks very much, Josh. Looking forward to chatting with you about Pyretic today.
Likewise, Nick.
Cool. So, what led you to work on Pyretic, and what do you think are the most interesting features it provides, or the most important problems that it solves?
Okay, so let's see. First, Fortuity. I was doing my PhD at Columbia, working on a variety of sort of network meets systems kind of stuff. And then I was fortunate enough to get a CI fellowship, and that was to Princeton to work with Jen Rexford. And Jen and her collaborators at Princeton, Dave Walker in programming languages, and also at the Cornell, Nate Foster in programming languages as well, we're kind of had this ongoing work on sort of software-defined networking, languages. How do we put these two together, provide an interface, set of abstractions that are kind of coherent, intuitive, powerful, that can actually potentially be used in practice and make real impact on the community. So that's sort of the high-level vision and goal of what they were aiming for when I kind of came in and joined. And I was immediately sort of with my sort of systems meets networking background and taste, wanted to see, okay, well, what can we do to push this forward in ways that are going to be most appealing to folks who might actually adopt this technology, practitioners. And so at the point where I joined the program, this wider collaboration called Frenetic, which I think we'll be talking about a little bit later, they were really focused on a lot of the sort of deeper, more core PL kind of issues. They were doing an implementation in Haskell, a functional programming language, which is fantastic. A fantastic language, but it's not one that's necessarily intuitive or familiar to the systems community. So I immediately said, well, I'd love to see this in a language which is more accessible, both to the systems community, folks who are already programming, and potentially even to folks who are currently doing network operations. These folks might not be programmers, but maybe we can package this in something that they'll have a relatively smooth learning curve on. And functional programming can be a big jump. It's a really powerful paradigm, but it's not intuitive at first to the vast majority of us. So I, along with some other folks, some students at Princeton, and working in conjunction with Jen, Nate, and Dave, decided, okay, I'm going to lead an effort to provide a Python-based version of the sort of concepts and ideas that we had in the Frenetic project when I joined, and also push forward on a variety of different fronts that I thought were particularly important and that appealed to my sensibilities as a researcher. So those were modularity, number one, and then also, how do we put this? Mechanism agnosticism. Maybe a bad word, but basically the idea that we want to get further and further away from mechanisms when we're talking about a higher level language for describing how networks should behave, and then leave it to the runtime system compiler to figure this all out. So should I keep talking, or did I answer the question?
No, that said a lot, certainly. I guess, because one of the things I wanted to ask was, about the features that made Pyretic interesting, and I think definitely you sort of made a nice distinction between the earlier work going on that was more functional and Pyretic, and I guess you also headed off my next question, which is how Pyretic relates to some of the other things in the Frenetic family, like Frenetic and NetCore. I guess one follow-up there is Frenetic is based on this NetCore compiler, and I guess Pyretic is as well, right? I mean, in some sense, is that the case?
Yeah, sort of. It gets really, really complicated because the Frenetic project, umbrella project, a collaboration primarily between Princeton and Cornell, though at this point other researchers and other institutions, including I think your own, have gotten involved in some of the work. And the high-level goal is what I described before: provide a language with abstractions, or a family of languages really, that provide these kind of high-level abstractions that are intuitive, and then leave all the details of figuring out how to implement this and realize this in a given particular network with its own particular topology and set of hardware to some piece of computational machinery, which we call a runtime system and compiler. So the sort of big that's the big umbrella. And where things were when I joined, there had been sort of a very early system which was called Frenetic, and that system its key idea was, hey, let's try to do a functional reactive programming approach to network control. And functional reactive programming is a really neat type of programming language thing. And basically the idea is it's designed to take streams, each stream being composed of a series of discrete events that come in, and as each event comes in, there's some machinery which kind of whirls around and passes on to something else and whirls around, and then so forth. So in the original kind of design, there were three sort of sections. There was a section that was doing that provided a sort of query language, and this was very SQL-like. And then there was another section which let you do forwarding type things, and then there was kind of a glue between that with these various FRP, functional reactive programming operators, and hence the name FRP network Frenetic came to be. So things evolved. The next kind of step along the way there was looking at the notion that, okay, maybe this FRP stuff is a little bit over heavy, but in the forwarding portion of things, there are actually some very interesting things going on. When we look at forwarding, we look at querying. Namely, we might want to do these at the same time. And in fact, when you're doing querying in an OpenFlow-based network, you're actually reading counters off a table. So this is not like using a tool like NetFlow or SFlow, where you've got an entirely separate stack of software or firmware running on the switch, which is going to be gathering these statistics. But instead, you're actually going to be inspecting the very tables that are used for forwarding. So if you change your forwarding, you potentially can remove entries from the table, and thus that affects the counters, and that affects what, in fact, you can query. And so, they kind of moved on to this key idea of, hey, we can do some type of parallelization. We can provide a way of specifying some querying and a way of specifying forwarding that enables you to write lots of things that work in parallel. And that was really cool. In fact, there's sort of, you can have as many readers as you want. One writer clearly makes sense. You can also do two writers, but you might get sort of strange behaviors out of that. At least when parallel composition is all you have. So that work really spawned, what was really cool about it, in addition to what I said before, is also they came up with a really sophisticated way of taking these parallel composed specifications of reading state of the network, so querying counters, and writing state of the network, which is to say specifying how packets will get forwarded, and compiling that all down to a set of OpenFlow rules on a bunch of switches, and having it semantically, so its meaning, its actual behavior, exactly matching the syntax that they described. Okay, that wasn't the most eloquent way of putting it, but
you get some provable properties then, I guess, or you have the ability to kind of reason about. You write this thing at a high level. You want something good to happen, or you want something to happen that kind of matches that policy, and you have a way of saying, like, okay, what's happening in the forwarding table is actually semantically the same as what I write in this high level language.
Yeah, exactly. So you basically, the language provides you with a syntax, a way of writing things, and then you can write things that have completely specified meanings. And what you're getting at here, I think, and what was really another thing about this that was really neat, is that beforehand, if you look at sort of like POX or NOx or Beacon, Floodlight, these kind of languages, generally you have to specify independently how packets are going to be treated on the controller, so what we'll call an interpreter loop, and how packets are going to be treated on the data plane, so what the OpenFlow rules are going to be to handle them. And it's not necessarily the case that you're going to get it right. You have to specify this logic in two different places, and the results may not be the same.
I think even in the course, like as people were doing the assignments, they had this confusion of like when I'm writing a learning switch, like I'm writing this thing that keeps a table of mapping like MAC addresses to destination, to output ports, and they're like, wait, that's happening at the controller. It's not actually on the switch, right? So I think there was some like cognitive dissonance there. That it's exactly what you're pointing out.
Yeah, and I mean it's just kind of a thing that's automatically gonna cause your code to be more error-prone, more complicated, more convoluted. So what was really neat is with a single syntactic representation, you both had an interpreter that realized that when packets came to the controller, because they were directed there either because rules hadn't got installed or because it was part of a query that needed the packet or whatever, and also provably compiled a correct set of OpenFlow rules that realized that exact same behavior in the data plane. So you knew what was going to happen on the controller and what was going to happen in the network switches. You'd always get the same results. And that's a great property to have. That's a really important one. So that was kind of the past, or the situation when I came in. And what we really, and each kind of iteration in the family of frenetic languages, early on they were all named frenetic until NetCore. So let me quickly describe what NetCore is. So one thing that was realized is, hey, we can really think about the way in which the network's behaving, the packet processing behavior of the network, which we've called in our body of work the policy. So policy is how the data plane forwards, how the data and control plane forward packets, and also send packets to the controller. So it expresses when a packet comes into the network, exactly what's going to happen afterwards in the next step and the step after that and so forth until the packet, or all of its descendant packets, if we're, say, doing a multicast, leaves the network. So NetCore is a static domain-specific language. And by static, I mean that it specifies the packet processing behavior or policy on the network for one given instant in time. And if that behavior is in fact changing, we can consider this a series of static representations. So I'll have my first static representation of how the network behaves, then say I'm going to change how the network behaves on one particular link. I'll make a new representation, put that one in effect, and so forth. So NetCore gives you this language for representing how the network behaves in a given instance. And then when you embed that in a higher level language, like a generic language like Python or Haskell or OCaml or whatever, you can use the language's data structures and flow control and whatnot, your while loop, to create a series of these static things and then make each one effective in the network and thereby create your kind of dynamic behavior. And so this was the approach that was kind of adopted by all the work going forward, at least up until recently. And I would say even recently, but we'll get to Kinetic hopefully a little bit later. But now coming back, so at the time that I joined, NetCore was really just this, we can write a query or several queries, and we can put that in parallel with, some forwarding policies or some forwarding policy components. So I could say how one switch forwards, how another switch forwards, run those in parallel, and then I've got a policy that covers the behavior of the two switches. So Pyretic basically, started off and said, okay, well this is great. Let's get all this NetCore goodness implemented in Python, embedded in Python as well. So when I say embedded, it means when you write a Pyretic program, it's actually a Python program that has some extra syntactic elements, namely this NetCore, as we'll call it, domain-specific language, and a couple of other goodies. It's also implemented in Python in the sense that we could have written an interpreter that takes this Python code plus and then compiles it and manages it using, say, C++ or Haskell or whatever. But we also wrote it in Python, so hopefully it would be very accessible and easily changeable and understandable by the community. And that was one of the real aims of the code base. And then we started thinking, okay, what are the research problems here? And there were a couple of new things that Pyretic introduced into the family of phonetic languages that were then absorbed by the members of the family that survived. Right now, the surviving descendants are basically Pyretic and a version of phonetic written in OCaml, which I like to call phonetic OCaml, because I'm a little bit picky about naming conventions. What were the new things that we introduced? Well, the first and probably the biggest one was previously you could write one component of logic and you could write another component, and you could run them at the same time on the same packet. And what you get out is the set of packets produced by the first one and the set of packets produced by the second one, union together. But that's not the way a lot of things we want to have actually work. That doesn't give us the ability to express something like, say, hey, I want to write a load balancer. It's going to take a packet coming in and rewrite its destination address, for example, to map it to one of several servers down the line. And then I want to hand that off to a routing module and have the routing module act not on the original packet, but on the packet whose header has been remapped. And so this is an example of a different type of composition, sequential composition. And you'll actually find this type of composition in the underlying hardware. So there are multiple tables in switches usually, not just one, like the original version of OpenFlow provided. So this is a very natural kind of way, and other work has thought about this in terms of data path pipelining and so forth, and this was missing. So we introduced a new operator to the NetCore domain-specific language that enabled us to do sequential composition, and it's semantics work. So in NetCore, everything is a function that takes a packet at a particular location and outputs a set of packets at particular locations. So, take a packet at switch on port 1, output the same packet at switch on port 2, that's forwarding. I could output 2 packets, one on port 2 and one on port 3. That's multicasting. No packets, that's blocking. A packet but with a header changed, that's, field modification. Renaming that could be used for balancing. So basically, the semantic of sequential composition is very, very straightforward. It's basically if we have one function A, a NetCore function, and another function B, it's basically saying we're going to take B of A of the packet. And there's a little bit, more because it's possible that A could actually output multiple packets. So there's slight tweaks, but that's roughly the definition. And that's intuitively correct, or intuitively reliable. If that's your intuition, it'll work, and we take care of the rest of the details underneath the hood. So sequential composition was really big because it let us do all sorts of things. And it turns out that actually once you take sequential composition and parallel composition, and you have both of those in a language like in language design, the way we had designed NetCore, you actually get an instance of what is known as a clean algebra with tests. And there are all sorts of wonderful properties clean algebras with tests have, which are already proven. And so after we kind of published the Pyretic work, we were all kind of seeing, oh, there are a bunch of transformations you can always make that are always true. And the folks at Cornell picked this up and published a paper, really great, showing all the theory, all the axioms you could use to transform different statements in the Pyretic version of NetCore into other statements that are provably equivalent, and showing that this in fact is a clean algebra with tests when you add one additional operator. And so with the addition of that operator, they had what was called the Netcat language, a different, slightly enhanced domain-specific language that was born out of the Pyretic's version of NetCore. So kind of complicated, but pretty nice. And Pyretic right now still uses NetCore because the Netcat stuff is super elegant and really nice, but practically speaking, isn't necessarily the first thing we need to get done to get adoption.
What do you need to get done? I mean, what do you think?
Oh, yeah. I'll tell you about that in one sec, but I just wanted to finish the story. So Pyretic right now has its own version of kind of NetCore, and the frenetic OCaml actually is based on Netcat now. So, and I'm not sure exactly how they do that, but you should. I think you're going to be talking with Nate Foster soon, so he can give you all the thing on that. So in terms of adoption, well, so we wanted to get a couple of other things going that Pyretic kind of introduced. So one was support for virtual header fields. So again, a mechanism agnostic way of specifying how you want traffic to be treated. So we can tag packets and then act based on those tags. Instead of saying, oh, I'm going to use the VLAN, some bits in the VLAN header, or I'm going to use MPLS labels. Because there are a whole variety of issues that you can run into when you want to combine things. If I write two pieces of software independently that say, hey, I'm using this set of VLAN these set of VLAN values to mean one thing, and the other one's using the same set of VLAN values to mean another thing, then you're going to get collision. Likewise, if you want to try to port from a network that, say, supports VLAN to one that supports MPLS labels, oh, you're out of luck if you specify things in this mechanism independent way. So we kind of worked on providing an abstraction that the programmer can use to just say, hey, I'm demanding a header name and I want so many values in it and I'm going to use it. And then you can, each program can be written independently and the compiler and runtime system can figure out, okay, how are we actually going to realize this on the network? And what are the capabilities of the switches? So that was kind of one thing, trying to push forward more into the practical sphere. Another thing we really focused on, you sort of provide things which would be very useful potentially for practitioners. Another thing we were working on was, hey, this idea of having a stream of static NetCore policies is all fine and well, but how do we actually provide this in some kind of packaging that makes it easy for programmers to do? And what do we need to change in terms of the compilation infrastructure and the runtime infrastructure and the interpreter loop to make sure this works correctly in practice, or at least that it works reasonably correctly and reasonably efficiently? And the focus here is not on, say, proving that we never mess up on a given packet, but rather in implementing mechanisms which generally are performant and potentially extensible to sort of getting provable behavior if you're willing to pay the cost that takes in efficiency. Whereas, my friends on the PL side were much more interested in just, hey, can we provably have something evolve in such a way that no packet is ever ever treated by the first version and then the second version. You can do it, but it gets, but you may be ignoring all the performance issues.
I think one of the things too is Pyretic is based. It basically writes to POX, if you will, or sort of runs with POX under the hood. And probably I think certainly people taking the course, probably the first time they've seen POX, it might be the last time. Particularly if they're in industry, they're probably going to run off and be doing other stuff, like maybe open daylight stuff or something like that. Will Pyretic ever, or Pyretic concepts, will they ever, or language constructs, do you think they'll find their way into other controllers besides POX? Is that on the roadmap, or? Oh
yeah, sure. So I think so first of all, POX is.
And what are the hurdles, I guess, to making that happen? I guess is the other part of the question.
Totally. So first thing, POX is great. That said, it does have its limitations. The way in which Pyretic uses POX really is just as kind of a dumb pipe. Pyretic has its own topology detection built in. It has, its own packet processing built in. But what it doesn't have is it doesn't have all the hooks in the back to, say, set up SSH connections or TCP connections, TCP connections generally, to the switches, maintain those connections, turn OpenFlow commands that are going out or OpenFlow tables into actually packets that go across the wire, and do all that kind of low-level stuff. So we basically made a choice to say, hey, we're going to just use POX as our backend. So we'll have a bunch of commands or RCPs, which are basically OpenFlow that the runtime has available, but those will be realized by some hooks into POX. So in terms of that architecture, you could, of course, take the POX backend out and replace it with a similar backend written in OpenDaylight or any other kind of language. I think what we'd really like to do going down the line is just own the whole stack and take the middlemen out of the picture and go through the pain of implementing the connections to the switches. And there's some open source projects which are kind of moving there, and do the work of actually marshalling the packets correctly into the wire formats for OpenFlow 1.0 or OpenFlow 1.3 and so forth. And then, that'll give up
open source projects. Like what are those? The ones that will do this?
So let's see. There's a library called libfluid, I believe, that was recently released a couple of months ago now in some kind of hackathon, and they provide tools for marshalling and unmarshalling OpenFlow packets in a variety of OpenFlow standards with, I think it's mostly C++ right now, but I think they're doing bindings to Python and Java. There's also another set of code, the LuxCgen. That's like the big switch folks and some others, and they have some marshalling, and they also built an Indigo platform which does some of the connection stuff. Although the Python, especially the Python part of that, doesn't quite seem mature, and the document. I've had a little bit of trouble with the documentation, though. Honestly, I haven't spent a lot of time on it yet because I haven't had it. But so there are a bunch of these kind of things, coming up, and also another important point is that we might not always want to target just OpenFlow. There are a lot of other great SDN kind of interfaces.
That definitely brings me to another one of my questions, which was like, can you imagine other southbound APIs? I mean, there's like netconf, there's even like command line interface. There's all this bare metal switching stuff going on that OpenFlow might go out the window with some of that. I was at Cisco Live, and they had like their new Cisco, I think it's AIS. So I mean, there are potentially a whole lot of different options out there, and OpenFlow is a good one. I think it'll probably stick around for a while, but it may not be the one that wins out in the end. And yeah, being able to compile down to all those targets, I think is a great thing for future work. I think of it as just a more heterogeneous sort of southbound set of targets. So there's just more interesting work to be done in the runtime system and compiler. And also, if we get more, the set of things OpenFlow can do are somewhat limited, and they're geared towards right now the limitations of current hardware. It may be that in the future, I just heard that Intel's releasing some switching-centric chipsets that also have FPGA integration. So maybe we're going to want to, once we have that available, we'll actually want to increase what the surface language can do or add extensions and libraries. So if you're going to have certain types of hardware, well, we can let you say more powerful things in the domain-specific language. If you have stuff underneath in the southbound there that's like less constrained than OpenFlow, shall we say, does it have any implications for things like NetCore? I mean, does NetCore make any assumptions about this having this very narrow interface or
Yeah, totally. I mean, so the design of NetCore, so it has a lot of nice properties, and I could go on about like what's really cool about it. But when we were designing NetCore, and over the course of NetCore's evolution into Netcat and then beyond, we really have tried to be cognizant of what the limitations of the southbound interface are and what the limitations of the hardware are, because we don't want to say, hey, you can write anything on your, as a static policy in your network, and just boom, it'll work. Like because our switches can't do turn complete calculations or even close. And so if if you provide too much of if you provide too much expressivity in your domain-specific language, what ends up happening is, in order to implement that and realize that, you're going to need to send all the packets to the controller. And then you're going to just kill your performance, your latency, your throughput. You'll probably crash the controller. So people can write great programs, unencumbered, fantastic for the programmer, but there's no cost metric associated with it, and therefore it's not practical. Now, there are potentially other ways of getting around it, aside from sort of having the switches themselves enhance the API. You could imagine an architecture where you have, additional devices that are embedded in the network that act as localized controllers and have potentially a quicker feedback loop with the hardware. That said, there are also certain limitations to the hardware right now. The TCAMs in today's switches are not designed for having rule changes very quickly. You have a switch that has 1 million. I think this kind of state of the art is like, we give you order of 1 million entries in the TCAM, which is tremendous. But the rates that these switches support in terms of changing rules are like 3,000 rules a second. When you think of a 1 million rule table, switching 3,000 rules a second doesn't give you a lot of dynamism. That's slow to evolve. And so we have to be cognizant of all this kind of stuff. And so, if as the underlying hardware and the interfaces to the hardware kind of expand in terms of what they can do and what they can provide, I definitely think extending the domain-specific language, or perhaps coming up with entirely new domain-specific languages for doing this, is kind of going to be inevitable.
Yeah, that seems like a really interesting direction. Is like how these DSLs are going to need to evolve as the southbound APIs change. I guess just one last sort of area I wanted to ask you about is some of your more recent work on verification and things like that. I mean, speaking of evolution, I guess you've sort of evolved what these northbound languages, if you will, could do in this kinetic work. Could you say a little bit about that? The students are going to look at that as well. So.
Yeah, definitely. So, when we had Pyretic, and we released it, there was, people really liked it. It won the NSDI Community Award, and a lot of folks just started building stuff on top of it, which was tremendously gratifying. But once we had this kind of modularity thing and some, mechanism independence going on, what quickly became apparent was, hey, this is, theoretically this is mission critical software. Okay, we're academics, so maybe it's not actually mission critical yet, but we want to come up with ways that are going to be robust to specify these things. And we have a great thing going with NetCore, but it's static. So whenever we want to change something, we kind of have to, write a new static one and put that on the network. And what's the difference between the old one and the new one? How can some, just regular piece of Python code that's generating this stream be assessed, to predict its future behavior? Will it produce some NetCore policy which is utter nonsense at some point in the future? Who knows? Will it just stop producing things at some point and get stuck in a loop? Who knows? And from the perspective of a programmer, how should I structure this mission critical code? What's the right way? How do I want this thing to look? So it became clear some abstractions for dynamism, for describing how the controller behavior evolves over time, we really need it. And that's where the kinetic work came in. And I joined this work when it was already in progress, and really, I've been very gratified to participate in it. And basically, the idea in kinetic, which is really neat, is, hey, why don't we provide sort of a natural, computationally powerful, but not too powerful, not Turing complete, and well-accepted mechanism. I mean, Leslie Lamport, I think, said this about finite state machines, or state machines in general, maybe, that, hey, this should just be the basis of computer science, computer programming. That's all we should ever use. It's this really neat note. You should totally go look it up online and read it. But coming back to right now, the idea in kinetic was, hey, we could use finite state machines as a way of describing dynamics. So each state in the finite state machine would have some NetCore policy in it, so a static policy which is associated with that state. And then based on events that happen in the network, like say I see a particular packet, or I get a warning from an outside intrusion detection system, or the stock market, goes down by too many, points. I transition to my next state where there's a different NetCore policy, and that NetCore policy might be, like, oh, block packets now, or oh, route them a different way, and so forth. And so once you have this kind of structure, it enables a bunch of really neat things as well. So it's intuitive to the programmer, which is where this FSM was originally introduced. But one of the observations that we made was that, hey, this gives you a structure that we can use for actually verifying certain types of properties. So there are techniques and model checkers out there that'll let you take a finite state machine and write statements in temporal logics. So these are, logic like you're probably familiar with, if A, then B, B and A, not B, etc. And add to them some operators specifying time, things about time, like, for all future times, such and such condition must hold. Or if I have a branching tree of possibilities of different ways I might traverse through my state machine, then there exists at least one potential future path in which such and such could happen. Or there exist no paths in which I'll get stuck in such and such state. And so you can make these statements in temporal logic and then use a theorem prover, an out-of-the-box model checker like NewSMV, to actually show that, hey, the program you wrote in Kinetic, which we implemented as a library on top of Pyretic that provided a DSL for writing these state machine things, this can be directly compiled completely by heart, completely by code, so no human intervention, to a model that NewSMV can take, and you can write your temporal logic, and then NewSMV will tell you yes or no. And if it says no, it'll give you a counterexample for the property that you specified. And this was really cool and powerful, and we were able to build a lot of really neat applications with it.
It's super neat. Like, I mean, I've seen some of the policies as well written out, and I'm going to show the students some of them as well. Like, super neat. Like, you can say, like, okay, if an infection event happens, like, you'll eventually transition to this other NetCore policy that's going to do dropping. So it seems like there are a lot of things that you can definitely verify. Are there things that you can't verify with Kinetic? I mean, it seems to me, I was kind of looking at it. Can you say, for example, like, I mean, you can say, for example, like whether or not a state is going to be reached, but can you say things about, can you make assertions about flows or reachability, or is it one level of indirection away? Is it possible to do that?
So it is a level of indirection away. I mean, so there are a variety of limitations to the kind of statements you can make. Namely, anything you can't express in CLT, you can't express, you can't prove. That's kind of the formal version. But in terms of properties, so the properties you can state are ones about the evolution of the state machine. But since each state in the state machine is also a NetCore policy, and NetCore policies themselves have particular characteristics that can be proven about them, it's possible to, right now, do some hand proofs provided combined with new SMV.
Some, like, automated proof of like what states can or can't be reached, and then from there do your kind of like.
And then you have another proof mechanism for, say, showing like, oh, each one of the NetCore policies in each of the states preserves something.
Do you think the whole thing could or should eventually be automated, or?
Oh, that would be so cool. I think that's like a wide open research question. I've definitely chatted a little bit about it with Sharad Malik at the E department in Princeton, and he thinks it would be really cool to explore. I mean, part of the question isn't, whether we could, I mean, with proving things in general, you can always not always, but the vast majority of the time you can do a brute force thing, like explore every possible thing that could ever happen, and as long as there aren't an infinite number of those, eventually you'll get an answer. But there very well may be a class of things in between that we can specify that are broader than simple temporal logic properties, but at the same time narrow enough that we can say something about behavior in the network data plane that will always hold in certain types of ways, given we have this particular FSM and it evolves in a way that prohibits certain types of evolution.
Interesting. Yeah. So so one final question I thought is what do you think the sort of killer app for adoption will be for Pyretic? Do you think it's sequential composition, or do you think it's this verification stuff that you've added to it with Kinetic? Do you think it's just something else that hasn't been done yet?
Well,
what do you think is, if there's one thing that would make people say, like, I must have this, what would it be?
Okay, so I mean, I think it's I'll make a distinction between feature set and application. So over the course of the Frenetic project, from that earliest FRP version coming to Pyretic and then Kinetic, forking off into Frenetic OCaml with their own stuff, there's kind of been this buildup of good abstractions and good features for doing things. So being able to say things that are useful, being able to realize them in the network efficiently, being able to provide various types of guarantees to the programmer or network operator. And I think, each way, parallel composition was super important. Sequential composition, super important. Oh, one thing I'll just quickly mention that Pyretic did that I had kind of left out before, we kind of got rid of the SQL-based querying language and instead said, hey, querying and forwarding can be considered as just one thing, where instead of forwarding a packet out of a physical link on the data plane, we're going to forward a packet out of virtual, port to the controller or to a data structure on the controller. And so we introduced this notion of buckets also in Pyretic, which I totally missed talking about before. But this was a big step forward in terms of a unified way of writing things. And so as we add each of these features, we enable potentially a wider range of applications that can be efficiently implemented, intuitively expressed, etc. And so it's hard for me to predict exactly which feature in the language is going to be the one that kind of tips the balance and really makes this super real and practical. I don't know if there is one, but I think my approach has been to kind of try to add these features and also libraries like Kinetic and potentially other libraries that provide useful general purpose facilities and hopefully get ourselves there. And I mean, even in terms of Pyretic right now, that SDX work was done on it, and that stuff seems to be catching fire right now. So, maybe we've already got some killer applications.
I think you hit the nail on the head, which is one of the things I think as people use it too, especially after sort of grinding it out with POX, is you do one thing in POX, you do the other, you do the same thing in Pyretic, and you're like, wow, okay, I don't have to think about all these things about where the state is, and oh, I can compose these things so easily, and now you get verifiability as well in certain aspects of the program. So
yeah.
So I think maybe, like you said, maybe you're already there in some sense.
Yeah. Just one little thing, we should not beat up on POX. POX is really awesome for what it is, and
Absolutely.
it's very similar, in fact, to a whole variety of other Ryu and Nox and Beacon and Floodlight, and I'm going to say Open Daylight, although I might get some people who then do that whole firebombing me on the internet because Open Daylight is different and better or something. But I think fundamentally they're first order approximation. They're all very, very similar. So POX is stand-in for that whole family of what I like to call OpenFlow centric controllers. So yeah. Mm-hmm. Anyway, that's my own little whatever.
Cool. Well, thanks a lot. Yeah, thanks for chatting about Pyretic today and Kinetic, and looking forward to using it more and building lots of cool apps with it. So thanks.
Awesome. Thanks so much, Nick. I really appreciate you having me on your show.
Yeah, it's a course.
I guess we go to the call lines now.
Yeah. Yeah, exactly. Oh, was that a phone I saw? Okay.
Yeah. I'm in a hotel right now, and it has a phone. It had a phone, so I decided to pick it up and be like, "Oh yes." That question isn't about. Anyway, I won't do my comedy routine now.
Cool. All right. Cool. Thanks a lot.
Thank you very much. And yeah, talk to you soon.
Thanks.